So I want to talk about the weight filtration in the monodromy theorem. So this is Grothendieck's monodromy theorem. Okay, and these things can be thought of as being kind of the way I like to think about it is they're kind of like the Weil conjectures in characteristic 0. So we're going to be doing a lot of the same things. So first, let's fix x over q, smooth projective variety. And what we can do is we can consider the representation. So the p-adic representation associated to this variety. So what we can do is we can take the absolute Galois group of Q, and we can map it to the automorphisms of H, I, and then what we do is we act on, we base change. So in this video, Q bar is going to denote the algebraic closure of Q. And then we act on QL. So this is p-adic cohomology, and this gives a Galois representation. Okay? We can actually restrict this to QP. We can restrict to QP, but before that, let's talk about QP, the absolute Galois group of QP. So here, there's QP, the absolute Galois group of QP, we have this kind of specialization map where this goes to the absolute Galois group of FP. And then there's the kernel of this, which is called the inertia. Okay? So this is the inertia subgroup. And in order to state the Grothendieck's monodromy theorem, I need to talk about the a certain character on inertia. Another thing to say is that in local class field theory, when okay, so this part here is z hat. It's generated by the Frobenius here. This guy is an extension of z hat by this thing, and when we take abelianizations, this thing becomes the units. Oh, so sorry. This is supposed to be QP here. So this becomes the units of QP by local class field theory. This is the valuation here, and then this becomes the units of QP star after we abelianize. All right, but that's not what we're going to do right now. We're going to talk about a different character that I want to talk. So we need to. So let me just say this again. So to describe to set up Grothendieck's monodromy theorem. We need to give a certain map. Okay? And this is going to be the Tame inertia character. Okay, so this is the arithmetic Tame inertia character, not to be confused with these inertia characters that come from the, neighborhoods or formal completions of curves at points, and looking at like decomposition groups and these sort of things. All right, so we need to talk about this. So again, there's kind of two parts to the inertia. So let me just say that this is about the Tame inertia character. That's what we're going for here. Character. Okay, so this inertia has this pro-p part inside of it. This is the pro-p part. And so this is the so-called wild inertia. And if we take the quotient by that, So this is the so-called Tame inertia. All right, and this is the thing that we understand well. This is the part that the wild inertia is the thing that we don't understand well. So, associated to these associated to these groups, there are corresponding extensions. So if n is a number that doesn't divide p, we can form a field, Kn, which is Qp, where we adjoin an nth root of p. Okay? And it turns out that we have the following, that the Tame extension here, so this is inside Qp bar. Okay, so this thing is the unions of these Kn's for n prime to p. Okay, and for each of these Kn's, we have a character which will okay. So for each using the uniformizer, so this is a choice here, we get the Tame inertia character, and it's given by the following. So this is a quotient of the Tame inertia group. Okay, so now we have this unramified one. So I don't know if I said this, but this is the same thing here. Okay, so there's unique lifts of the Frobenius here. Okay, so there's this thing has all the roots of unity, by the way. So this guy, there's a map here, TPN, here, to mu n QP times, like this. Okay, and what it does is it takes sigma, and it maps it to the exact thing we did for the geometric inertia character here, like so. And this is p to the n, like so. Okay, and this defines this is the Tame inertia character at finite level. And these fit into a system, okay, which give the full inertia character here, TPN, and this goes from QP Tame over QP unramified to Z hat 1 dagger. And so this dagger means this is the prime to p part. Prime to p roots of unity. Okay, and that gives us this Tame inertia character. So, in particular, maybe I could call this, actually maybe I shouldn't call this TP, but maybe I should call this T hat. Okay, so in particular we can look at a P part of this. So, for a prime L, we can consider these maps. So TL. Here, this goes from I. So this will just be the prime to the L part of this. Here to ZL times CL1. Okay, so this goes from here. I guess this is, maybe I can do it like this, Tame. All right, so this is all I wanted to say, and now I can state what Grothendieck's theorem is. So there's the theorem. This is Grothendieck's monodromy theorem. It says the following, so if x over q is a smooth projective variety, so there exists some n, so this is a nilpotent endomorphism, hi xq bar ql. So this is nilpotent, such that if we look at the representation associated to x, so I wrote this down. So this is just this representation, and it's given by acting here. Okay, if we look at the induced representation here, and we take it on some sigma. Okay, so this is the representation associated to x, I guess. And maybe it's at the place L. So this is the, it turns out that this is the exponential if we take the L Tame inertia character to n. Okay, so this is what it says. It's a structure theorem. So a proof of this, a proof of this, I guess for open subgroups of the Galois group is can be found in Serre-Tate on ordinary. They have this paper on ordinary abelian varieties where they do this Tate twisting and things like this. Okay, so this is where we can do this, and then I'm not going to do this in this video. Okay, so we have Grothendieck's monodromy theorem, and it gives us it tells us about the structure of these L-adic representations associated to L-adic cohomology. So it's a fact that linear algebra, so just from linear algebra, from the structure theorem, using linear algebra, so it's kind of an inductive argument. We get we get the weight filtration. We get this a so-called weight filtration. Okay, and so let me define what this is. Okay, well, definition, maybe proposition. So given n, this nilpotent operator on, let's say, V, which in our case is equal to hi x, let's say hj for now, xq bar ql, what do we get? We get there exists some wi's in increasing filtration so by this I mean wi minus 1 isn't wi plus 1 of subspaces of V such that 1 the operator on Wi sends it to the lower guy. Okay, so it's decreasing here. So this guy shrinks this guy, and that if we raise this to the ith power, and we look at the ith graded piece, this will induce an isomorphism to the minus ith graded piece for I greater than or equal to 0. And then let me just make a little remark here that this ith graded piece here is just one of the guys minus the previous one. So it's a subquotient. The graded ith piece is a subquotient of the w-ith piece. Okay, so this sends this to this, and then it induces an isomorphism here. So I'll put a reference to this in the comments. Okay, and so the Weight-Monodromy theorem is a theorem of, so there's this theorem now. So now, okay, so this is the weight filtration. This thing that's cooked up from the monodromy operator. Okay, that's the weight filtration. And now there's a theorem, and it's due to recent work of Scholze. Hopefully, I don't know if I'm saying Peter Scholze's name right, but it's built on a lot of earlier work of a bunch of other people. Okay, and it says the following. It says that if F in GQP is a lift of the Frobenius, and I guess this is the geometric Frobenius, which is the inverse of the Frobenius, and alpha is an eigenvalue of the Frobenius on the ith graded piece of the jth cohomology. So this is the jth p-adic cohomology that we were talking about before. Then we have the following. The first thing is, so this is like the Weil conjectures, like I said. It says that this number is actually an algebraic integer. The second thing is that the Archimedean norm of this has a certain size. And so this is like the Riemann hypothesis for varieties over finite fields. And it says that this is j plus I divided by 2. Okay, and so this is the, I guess, the weight. So this was a conjecture for a while, and I guess this is proved for, so this is, I guess, for smooth projective. he phrases it as being in terms of x inside a toric variety, but then projective space is a toric variety, and then those are a lot of examples, and I think it's just easier to state it this way. Okay, so that's this is the thing, and this is why this is like this is kind of like a higher dimensional or characteristic zero Weight conjectures. So this is some sort of mixed characteristic thing. Okay, so let me just make some remarks about the proofs. Okay, so let me just make this real quick. So the case where j is equal to 1, so this was Grothendieck. J is equal to 2. This is Rappaport-Zink. And then combining results of de Jong, de Leon, so this is the Weight conjecture stuff, and Grothendieck. Okay, you get that the absolute value here looks like p to the n over 2 for some n. So this is kind of like a similar situation to where de Leon was when he was proving the Weight conjectures. And then you also get that alpha is an algebraic integer. Okay, or an algebraic number. Okay, so and then the Scholze's technique did the rest with his crazy with the crazy perfectoid tilting trick. Where he reduced, so he reduced the mixed characteristic case to the equicharacteristic P case. So reducing the mixed characteristic case to the equicharacteristic P case. So equicharacteristic means that, you know, the field and the residue field have the same characteristic. Mixed characteristic means that you're looking at something like QP. To the equicharacteristic P case, but here you have to do things that are really ultra ramified. To the equicharacteristic P case, where the result was known.